So thank you for the invitation. It's really nice to be here and talk about MHD, which is what I normally do. I normally talk a lot less about geophysics. So I've got a bit of a challenge here talking about MHD approximation in geophysics. So feel free to help me out. So why do we need one? Well, if there wasn't a magnetic field in the Earth, it would look perhaps like this. So that's the outer liquid core of the Earth, and this is the region we're mostly interested in. Because the Earth rotates very fast, the effect of rotation, I'm a bit short-handed here because I thought this would be covered this morning. But so there you go, I'll do it. So one of the main effects of rotation is to preclude variations of physical quantity along the direction of the rotation. So that's the Taylor-Pridman constraint. So that means the velocity essentially should be almost invariant along the direction of rotation. And also, the rotation prevents flow from escaping following a divergent path across the direction of rotation. And so the remaining motions should be of order Ekman and Rossby. And for the Earth, Ekman being 10 to the minus 15, Rossby 10 to the minus 6. So this is practically nothing. So what you should have, really, is two different regions. Either side of this tangent cylinder, this is called like that because the tangent cylinder is extruded along the inner core. And the reason it's so important is because if the flow cannot vary along the height and cannot diverge, it has to follow contours of constant height. And there's a big jump in height between here and here. So it's very hard for the flow to cross that boundary. So we have convection with a hot source here and a cold boundary. What did it stop working? Cold boundary here. But because of this boundary, we should have two different types of convection. And here an experiment shows what you should have here is elongated column because of this constraint. And also here elongated column, but with a temperature grade, a gravity going this way and temperature gradient going this way. So the main, I think John mentioned that this morning, the main difference between the two regions is that here the rotation and the temperature gradients are aligned, where here they're perpendicular. So there's the two different regions. Here you get this nice column, and here you get more so Rossby waves, zonal flows, and turbulence. So these are two different regions. And that has been seen in experiments, a number of experiments. But the question is, of course, the Earth has a magnetic field, and this is a picture that does not account for the magnetic field, and it has also a highly conducting liquid metal here. So the magnetic field will have an effect. So what happens to this picture when we try to account for the magnetic field? So, and these are the questions that I want to discuss today. So the first thing is to identify what effects we can expect from that. And then if you want to try and study these effects, you have to try and reproduce them in a lab. And that becomes more difficult because laboratory experiments, as we learned this morning, do not run in the same regime as planetary objects. So the question is, what approximation can we use, and are they valid back into the conditions of the real the real planet? And that raised the question is, what effect can we actually capture this way? And finally, I'll touch on a rather broad question is, now that the Taylor-Pridman constraint tells us how rotation constrains the flow, but what if you have a magnetic field? What is the joint constraint? Because in the end, that all goes back to that. So, so the first, sorry, wrong button. Here. So what are the effects that we can expect in the core? So the most obvious, and I'll get this one out of the way because I'm not going to talk about dynamo, is dynamo. So there are plenty of talks about dynamo, go and see them. But it is important, of course, and the reason we have a dynamo is because at the scale of the core, the transport by the flow is much more efficient than any form of dissipation. So the transport, if you try to scale, you can easily calculate timescales for transport based on the size of the core. This is not necessarily the right timescale for the right length scale for dynamo. This is just really a rough estimate. And you can also evaluate dissipation, but here we have two types of dissipation. There's ohmic and viscous. If the ohmic dissipation being much more efficient, you can also estimate a timescale for ohmic dissipation. When you do the ratio of the two, you find that there's a factor at least 1,000 or of the order of 1,000, which means that the magnetic Reynolds number, which is the ratio of those two numbers, is large, and so that is a prerequisite for a dynamo. It's not sufficient, but it's a prerequisite. Now back to trying to reproduce this in the lab with convection, because the convection is what drives the motion. What you would need is a velocity that is sufficiently high, and how the velocity in a convective flow is, you can use the scale of the free fall velocity for that. And if you pull this back in there and you say you want a magnetic Reynolds number of about 1,000, you use sodium, which is the most conductive material, and a normal size experiment of 1 meter, well, you need pretty large temperature differences. It's very, very hard to do. For that reason, the only dynamos that have worked are not convective. They use pipes, they use von Karman flows, so it's sort of washing machine type arrangement, or a turbine. So these are phenomenal experiments and are massive milestones in the study of dynamos, but they're not very geophysical. So the other way is to break the 1 meter rule, and you go Franck's way and you build the most gigantic MHD experiment ever built. So this is precession dynamo. That actually might be a planetary relevant when it works. When you say it works next year, that we said. So go to the dynamo talks. All right. Other effects that one might find is waves. So we have the magnetic field can carry waves, can generate waves, and there are several types of waves. So without rotation, there is an inherent type of wave that is associated to magnetic field. Essentially, the idea is that if you disturb a magnetic field line, the disturbance will propagate along the lines of the magnetic field, and that creates a wave. It's called Alban waves. It was discovered. It's a very simple form of wave. It was discovered in 1942 by Alban. That's why it carries its name. So that one could expect. It has a velocity that is proportional to the intensity of the magnetic field. So you tend to need higher magnetic field to get them. But there are also, because we have a rotating system, there are also variants on MHD waves that include rotation. And so, for example, torsional Alban waves are waves that do not propagate along the magnetic field lines. They propagate normal to the geostrophic contours. So the geostrophic contours are these invariant surfaces where the velocity has to stay constant. And if you have a very strong rotation constraint, then the velocity stays constant along that, and all the propagation that remains has to be normal to that. So this is a nice illustration by the Grenoble team of the wave front. So these are magnetic field lines. This will be the wave front of an Alban wave, so propagates along the wave. And here, this will be the wave front of a torsional Alban wave, so those funny waves that propagate along normal to the geostrophic contours. There are all sorts of other waves. So these would be axisymmetric, but there are also waves that propagate azimuthally, magnetochorus waves. There's a whole zoo of waves like this. What they all have in common is they only exist if the time scale for rotation is faster than the time scale of the Alban waves. Okay? So the ratio which I should have written is the Leonard number. This is one of the conditions is that the number is large enough so that those waves exist. Small enough, sorry, the waves exist. And to make things more complicated, because the field changes direction and intensity and we move away from the core, what is supposed to happen, what people think happens, is that you get Alban wave here, and you get torsional Alban wave, or magnetochorus waves here. So if you have a wave packet travels from the core to the core mantle boundary, but the wave changes nature in doing so. So this is the sort of effect we can expect from magnetic field if you have rotation as well. Okay. Another one. The Taylor-Proudman constraint assumes that rotation dominates. That's the base assumption. But of course, if you have a strong enough magnetic field, there will be a Lorentz force that violates this assumption. So there's no reason for the Taylor-Proudman constraint to hold. And if you look, these are inversions. So these are inversions of satellite measurements. This is from the review from Finlay from last year. And so that's looking from the pole down. And these are essentially streamlines. This is the tangent cylinder. As you can see, the flow does not follow the tangent cylinder. And it breaks so that means the Taylor-Proudman constraint is essentially broken. And it's broken in two ways. There are very large scale and slow gyres. And you see that doesn't follow concentric cylinders. So that is a clear violation of Taylor-Proudman constraint. And there are much smaller scale oscillations here, which are probably due to waves, and they don't have the same time scales. So there are effects. So their origin is not known. There are a number of possibilities for the existence of these things, but the presence of the Lorentz force is one of them. I'm not stating that it is the definite explanation, just to be clear here, but it is one of them. Okay. And finally, convection. So this is what Suzanne was talking about this morning, Nakagawa's experiment. So this is a diagram, a stability diagram for the onset of convection in a Rayleigh-Bénard configuration. So hot here, cold here, and some nice liquid metal in between. This is a picture of Nakagawa's experiment in 1957. You can see that there is a minimum. So that line here is what you get without magnetic field. So, and this is for rotation of the order of the Earth. So you can see here that without magnetic field, there is a minimum critical Rayleigh number for a given wave number here. But if you start varying the ratio, so the Alsacian number is a ratio of Lorentz to Coriolis force, so the greater Alsacian number, the more Coriolis force. You see that the curve starts to separate. There's a second minimum that appears here, and the minimum becomes lower and lower and wider up to the point where it is located at a much lower wave number and has a lower critical Rayleigh number. So here, at this point, you start to have an onset not through this mode, but through a much bigger mode. And if you continue increasing the Alsacian number, then the critical Rayleigh also lowers. So the convection starts more easily and with bigger cells. But then if you continue increasing the Alsacian number, that maximum becomes wider and higher. So at some point, you lose it. You lose it's not the most efficient mode anymore, and you're back to the purely rotating one. The reason for that is that at some point you have too much magnetic field. There's lots of dissipation in the system, and all the magnetic field does is damp. So there is a sweet spot for the Alsacian number. So here in this diagram, it's between 10⁻⁴ and 4. It's a pretty wide sweet spot where convection starts with a different mode at a lower Rayleigh number. Okay, so another effect of, so that's the four main effects that I was going to discuss. And of course, now the question is, if we want to reproduce that in a laboratory, where we're constrained by the size of the experiment and the wrong direction of the gravity and all sorts of problems that you get with actual experiments compared to Earth, what regime do this experiment will operate in? How do we describe them? And do they capture any of these four effects, apart from dynamo? Okay, so we need a set of equations to describe the electromagnetic part of the problem. And start at the beginning. Of course, we start with the Maxwell equations. We're talking about a conductor. So these are Maxwell's equations. We're talking about a conductor. So that means that in Ampere's law, this term is the one that matters. And that means the displacement currents are not important. So this is typically the case with liquid metals. They have high conductivity, low permittivity, and also the system we're talking about operate at low frequency. So the way to break that condition is if you put water in a microwave, this term will become the most important because of very high frequencies. Or you work in relativistic condition. None of this applies to the Earth core. From this equation, actually these three, and Ohm's law, one can eliminate the current and the electric potential to obtain a transport equation for the magnetic field, and that is the induction equation. So here we have an expression of the magnetic diffusivity, which depends on the inverse of the electric conductivity and the magnetic permeability. I just mentioned, I will do that a few times because I'm a big fan of currents, that here we've eliminated the current. It doesn't mean that there are no current. And you will see that the current, I hope I'll convince you that the current is actually a very useful quantity to think about. So the current is always there in this approximation, and it can be expressed easily using potentials. But this is standard electromagnetism, you know that. Very important point. It may sound obvious, but I had this question. Because there is no displacement current, the electric current is solenoidal. So it is a very nice solenoidal quantity, just like the velocity field in an incompressible flow. And this is a very important point, that both behave in the same way.
Can I ask one thing really quick? If the
Sure.
electrical conductivity also changes in spatial position,
Yeah.
does that change anything? Because then the current can't be solenoidal. Or am I missing something?
Yes, it will change this equation. So these are indeed for an homogeneous medium. So you will modify this equation if you change the electric conductivity. That's correct. Yeah.
Well, delta J still equals to 0.
Sorry.
Delta J is still 0 with changing conductivity. Yeah. Because you just take the dot product of the first equation. That's what you get.
Yes, but this one will change. Yeah. Okay. Now, so that means for a full system, so we assume Newtonian fluid, incompressible, and electrically conducting. This is the system that will describe the flow. You note that I've sort of hidden convection here. There's an extra force. Of course, you need extra equations to describe whatever force you add, including convection. So whatever your favorite model for convection is, it will go here. So it's just the usual rotating Navier-Stokes equation with several differences. So the first difference, so here is the Coriolis force, okay? But the first difference is that there are two diffusivities. There are two sources of dissipation, the viscous one here and ohmic one here. So the magnetic dissipation is here. And then there are two ways to express the Lorentz force. One is you can use Ampere's law to express the current, or you can use Ohm's law. And so that gives essentially two philosophies. You can express the expression in terms of the current or in terms of the magnetic field. The advantage of expressing things in terms of the magnetic field is that you can eliminate, you have a nice closed system with two variables, U and B. If you express the current, then you need to introduce the electric potential, solve for the electric potential, but there's a price for that, and I will show you that later. There's an interest in doing that. Okay, so what physics do we find in these equations, apart from Coriolis force and dissipations? I mentioned dynamo. So the dynamo term essentially is this one. So this is the transport of the magnetic field by the velocity field. So that term is crucial. When that term is, you need that term to be significant to have a dynamo. Okay. We talked about waves. So where are the waves hidden? So you can recognize them here. So the purple, burgundy, purple terms. If you look at them, they look pretty similar. You have time derivatives in U and B here, and you have spatial derivatives along the magnetic field lines. So here. So two time derivatives. Now, suppose you have no inertia, no pressure, no dissipation, no Coriolis force, no convection, nothing, just those four terms. Then you recognize a very simple hyperbolic equation with a propagation in the direction of the magnetic field lines here, and a velocity that comes as, where is it? Here. The square root of atypical magnetic field divided by, the magnetic field divided by the square root of rho times mu. So that's your Alban velocity, Alban wave. So this is purely MHD, no rotation. So this is a purely MHD wave. And these are the four terms. So if you want to have MHD waves, you will need that term in particular. You will need that term in particular. So these two terms are usually easy to get. This one is the one that will give you waves. So if you remove any of these four terms, you lose the waves. Okay. Yeah, we'll come back to this point actually a little bit later. Or I could actually already mention it because we saw that you have a velocity here that is not the transport velocity, and that means that this term does not necessarily scale in the same way as the transport term. Okay, so that means that dynamo waves are different phenomena, they have different timescales, and that means you may need different timescales for those two terms. Yeah. Right. So how do I write this in non-dimensional form now, which is the more useful form of the equations? So as I just said, you probably want a different timescale for the transport and the time derivative terms. So I'm going to leave this timescale free for now. And for the rest of the for the rest of the variables, I'm not doing anything really fancy. L, U, B, J. You have a choice of two, whether you want a current or a magnetic field formulation. You can use either scales based on Ampere's law or Ohm's law, and that gives you two different types of equations. But there's not any preference for any of those. And at the moment, just use the standard rho U square for the pressure. But that also is something that can be modified to suit needs. So if you use those variables, then you get these non-dimensional numbers. So they are. So I've written this in an MHD way because, in a sense, I could have normalized by rotation, but I've normalized by here actually I've normalized by the dissipation. And you get those numbers. The reason I did that is because it gives you nice MHD numbers. So I have two screen parameters. So I don't know if you're used to screen parameters. They are typically the ratio. If you have an oscillating, if you have a quantity that oscillates and diffuses into a medium, the screen parameter gives you the penetration depth inside that medium against the global scale. So these come here. So and these are large if your oscillation is fast, or if your time scale is short. So two screen parameters, and they're different. Okay, there's a viscous one and there's a magnetic one. A very important point. Reynolds number, you know. I've got a Hartmann number. So Hartmann number is essentially a non-dimensional measure of a background magnetic field, or any imposed magnetic field scale. Magnetic Reynolds number, so that's the one that was very important for the dynamo, is the one that expresses the ratio of transport to dissipation. An Elsesser number, as I said earlier, is the one that gives you the ratio of Lorentz force to Coriolis force. And I think I've done them all. Okay, and of course you recover the usual Ekman-Rossby numbers as a combination of these. There's also a magnetic Prandtl number, which is a ratio of diffusivity, just like the thermal one, but this time with a magnetic diffusivity. Okay, so these are our equations. That's the full MHD equation. So if you have that, you have dynamo, you have everything, you have not neglected anything. So if you use those equations, you can probably obtain dynamos, provided you have a good enough code and you know what you're doing. Now, the problem is that obtaining a large magnetic Reynolds number in an experiment is difficult. You need high velocity, highly conducting fluids, or large scales. So it's not very easy. If you build a 10 centimeter scale experiment and your fluid moves at 0.1 meter per second, which is quite typical for a small scale liquid metal experiment, even with sodium, you're not going to have high magnetic Reynolds number. In fact, they're going to be much smaller than 1, and that means no dynamo. So unless you do something really on purpose and really specific and you have a lot of money, you cannot build a dynamo. So most likely you're going to do an MHD experiment that produces something else. So that means probably this U dot B term may not be entirely necessary. So there may be approximations that are a bit more restrictive and are probably better suited for the sort of experiment you want, in wave, for example. So so basically the question is, what happens if you have a small magnetic Reynolds numbers? What happens to the equations? So typically, this is what happens if you have a big magnet and you put your experiment in a magnet and you're trying to observe something. So you will have a background magnetic field, and the fluid motion will induce an extra magnetic field that superimposes to that background magnetic field. So to see what happens at low magnetic Reynolds number, I'm going to decompose these two fields. So there's a background field and a field that is induced by the flow. So B naught does not depend on the flow, B does. But at this point, I am not assuming anything on how big it is. I'm just saying that there's a decomposition, and I'm assuming that Rm is small. Then you can go with your different orders. So you go back to the equation, set, if I look at the Rm0, so order 1, the order 1 component of this induced magnetic field, well, you can see immediately that these two terms have to equate, and that decouples completely the induction equation from the fluid equation. So what it does mean that if you're not forcing your magnetic field with an inductor, for example, so that's typically what happens in industrial context, the field is going to decay away. So that means the order 1 induced magnetic field cannot be non-zero. And that means that even if you don't impose it, the induced magnetic field has to be order Rm. Okay? So the minute you assume that Rm is small, the induction is small. But that doesn't imply anything for the velocity. The velocity can be large. And then, if you want to obtain an equation, you go for the next order, and it's convenient to renormalize the B by Rm. And if you do that, so go back here, sorry. If I go back here, so if you put a 1 over Rm in your decomposition in here, what's left from that equation is essentially the same equation, but without the transport term. So that is a legitimate way of dropping the transport term. I say legitimate because it's very easy to just remove it from the equations. But with this approximation, you can do it with the right limit. Okay? So this is the low Rm approximation. And you note that very often the low Rm approximation is associated to no time derivative, no such thing, because I have a separate time scale for the time derivative. So you can have a time derivative here. You have lost your transport term. You can still have waves. You have no dynamo. Okay? That's the low Rm approximation. So what it does mean is, in theory, on a small-scale lab experiment that cannot produce a dynamo, you can still have Alban waves. And there's somebody here who's going to show you that on the poster tomorrow. The other thing that I would like to insist on, you can find an equivalent form of the equations in a number of papers that is obtained not by doing this, but by linearizing the system around a still state, zero velocity, and a given magnetic field. That is different. This is not a linearization. So this supports full nonlinearity. So you can have turbulence in this, okay? Whereas a linear system will not give you that. And the other thing about the low Rm approximation, Rm disappears because I've absorbed it by renormalizing here. But there is still induction. Induction is not zero. It's order Rm. If you have no induction, there is no MHD. Let's be clear about that. There's always induction in MHD. Right. Now, I said I kept this one, but I don't have to. So imagine now that I said the Alban waves are pretty hard to get because the magnetic dissipation is very large, so they will tend to stop the wave from propagating. And that means you'd have to have a short time scale for the Alban wave for them to exist. That means high frequency. And you don't always have that. So if you have a nice flow in a pipe, or you're trying to do a nice little convection experiment with a relatively slow flow, you may not have time scales that enables you to have Alban waves. So in that case, the screen parameter associated to the time derivative induction equation will be small. And that's another approximation. It's a step further than the low Rm approximation. So if you take that limit, so R eta, that screen parameter, goes to 0, then you obtain what's called the quasi-static MHD approximation. So quasi-static and low Rm are two completely different approximations. One implies the other. So quasi-static is always low Rm, but low Rm is not always quasi-static. Okay. So that is the form that you obtain. So another term drops. And that gives you a lot of possibilities. So the first thing you can do with that is you can actually eliminate the electromagnetic quantities by inverting this equation. You get this very nice equation here. And that illustrates the diffusive nature of the Lorentz force here, okay? Because when you do that, you've actually also dropped the gradient part. So this is a purely rotational part of the Lorentz force. So that has a number of numerical advantages. So if you're doing spectral method, this is very easy. This is just a multiplication. This is super easy to simulate, okay? And that means you don't even have to bother about coupling with electromagnetic quantities. You have built-in MHD just with one multiplication. So very useful and very fast. The other thing that is useful in this approximation is that the only variable that's left is the current. So the magnetic field is not a variable anymore. Only the induction is. So if you use the current formulation, there is an equivalent way of writing this equation. So there's a few steps. It's not completely obvious. Surprisingly, if you ask anybody who's been working in MHD for 20 years, they say, yes, of course, you can write an MHD formulation. But there's only one person who's actually written it down in a paper in a clear way, and that's Susanna. So if you want to know how to get that, you look at our 2022 paper. Huh? 2022? Yeah.
In the time-dependent case, you can also eliminate B. You just use a Green's function for the plus.
Yes, you can. Yeah.
I mean, for the...
Yeah, yes. The trick is, I don't think anybody's simulated that one yet. So I don't think anybody's done what you're suggesting. Yeah. That is also a non-local problem. It's always, the Lorentz force is always non-local. So physically, that's because the current recirculates in the entire domain. Yeah. Okay, so we get this very nice formulation, which is, as another advantage of the B formulation, is that the boundary conditions for the current are very clearly defined and straightforward to apply. Conducting, insulating, or anything in between, that's pretty easy to do by expressing the boundary condition directly in terms of the electric current. Okay, so these are the three levels of approximation: full MHD, low RM approximation, quasi-static. How am I doing with time? Very slow. Okay. All right. So the question is, what approximation apply in this experiment? So for that, I need to go back first to the different time scale that I'm looking at. I said I've left tau free. So what can we do? You can impose a frequency that forces the oscillating parameter to be large. That's brute forcing, essentially, brute forcing induction. That's, in that case, R eta becomes a control parameter. It's pretty straightforward. You can set to the turnover time. So if you do that, then R eta becomes Rm. So you automatically, if you're at low Rm, you automatically discard the induction, the dBdt. So if you impose this, and that is usually done without further justification, if you do this, you kill waves automatically. But then the question is, if you have no specific timescale in your system, you still have a potential Alban timescale. And if you choose that timescale, then this becomes the Lundquist number. And the Lundquist number is essentially the ratio of the propagation timescale over the dissipation timescale. If it's large, then the waves can propagate. If it's small, dissipation prevents propagation of waves. Now, we're talking about rotation. What can happen is that rotation is faster than both of these. In that case, you obtain a different number, and that's called the. So if you use the rotation timescale, you have a different number, and that number is the magnetic Ekman number. And what it does say, so this has to be the inverse has to be large for induction to be possible, and if you have that, then that means you can have induction by having an Ekman number is lower than magnetic Prandtl number, essentially. So with low Prandtl number, you have to rotate pretty fast. So typically with a liquid metal, you need to be under 10 to the minus 6. Okay, so that's the possibilities. Now, if you look at different experiments, so the Nakagawa experiment, you can do this order of magnitude, and you realize you calculate the Alban speed, the Alban timescale, the turnover timescale, and the rotation timescale. Alban timescale is the fastest, but the Lundquist number is very small, so there's no Alban waves, and because that's the fastest timescale, there's no other waves. So Nakagawa experiment is purely quasi-static. It's a good job because Suzanne's code is quasi-static and recovers all the results. So you can completely capture Nakagawa's experiment with a quasi-static approximation. And that means the shift from viscous to magnetic mode at the onset of convection is captured by a quasi-static approximation. Waves. So this is the DTS experiment in Grenoble. So it's a very cool, quite experiment with a magnet in the middle. And they've done a series of really nice experiments where they explored all the MHD waves with rotations. And the way this works, this rotates pretty fast. In fact, it's so fast that their RM is greater than 1. So in this one, there's no question, it's a full MHD. You need full MHD to recover that. But they have no dynamo. So in fact, you need much higher magnetic Reynolds number to recover that. And they do also recover the two regimes if you calculate the different types close to the core or here at the outer boundary. Because they have an Earth-like magnetic field, they find Alban waves in the center and various types of torsional, typically torsional Alban waves at on the outside. So they recover something which is completely Earth-like here. Brute forcing. So what do we do? This is the experiment that we did with Sami Laloz. So there's a cube full of metal, and the idea is that you inject current in a vessel, and you place that in a 10 Tesla magnetic field, and you put a super high frequency. So that's brute force. You get high frequency, high magnetic field. In fact, you can vary the frequency from slow to high. And when you do that, so here we vary the screen parameter. And this quantity here is essentially the attenuation between two walls. So we force at the one wall and we measure the intensity of the wave at the top. We go from, so the solid lines are the low RM approximation, the dashed lines is the QS approximation. And you can see that at some point they separate. And the data follows rather this one up to the point where it doesn't follow it. So what happens here when the data follows the QS, of course, we're in QS approximation. When it follows the solid line, we're in low RM. When it stops following it, in fact, this is linear. This is a linear approximation. When it stops following it, we obtain nonlinear Alban waves. And that's still low RM. The magnetic Reynolds number is 10 to the minus 6. So this is really, really low RM, and we've got nonlinear Alban waves. Okay? So really, if you were not convinced that low RM and QS are not the same thing, I think that should do the trick. But if you want to see far more fun things with Alban waves, go and see Sami's poster tomorrow. It will show fascinating things about that. Okay. Now, got a bit of time, okay? Do it quickly. So the last question I wanted to address is, I said initially that what really shapes the flow in a setting like the core is the Taylor-Pryman constraint, and it assumes that the flow is outrageously dominated by rotation. And now we're saying, well, the Lorentz force could be just as strong. So what happens? Okay, so this is very important to understand what goes on typically around the tangent cylinder area, because the field is mostly axial here. So that means the J cross B and U cross omega are going to be looking pretty much the same. The rotation and the field are aligned. Okay, so the two forces have similar shape and similar action on two different types of current. That's the main thing. So how does that change what happens at this boundary? Well, I'm going to exploit this similarity. So I've written the equations here to understand that. So here I use the standard rotating flow normalization with Ekman number, Rossby number. But I've written the equation in such a way that the Lorentz force and the Coriolis force can be put together into one. So you see U cross UZ. So UZ is the direction of rotation and the magnetic field. I assume the magnetic field is uniform. It can, I'm not assuming anything in terms of magnetic Reynolds number. So in theory, that would be the full RM, the full MHD equation. But I need to assume that the field remains mostly axial. So that limits the sort of induction you can have. You can't have very strong lateral induction. So it's not really the full MHD equation. But I've trunced so much of the equations away anyway that they all pretty much look the same at this point. So what's left is the balance between Lorentz, Coriolis force, and the pressure term. And I assume the flow is driven by buoyancy, but that buoyancy is not sufficiently strong to compare with those two forces. That's a common assumption for geophysical flow. And if you express that in terms of the convective Rossby number that was introduced this morning, it has to be small. Now, I said just earlier that we have two currents here. So you have a mass current and a charge current here. And they take the same form. But what it does mean is that when I write the equations like this, and if I introduce a current that combines both, actually I'll do it, combine both equations. So that current is necessarily solenoidal because the sum of two solenoidal currents. Well, I recover these equations, which are essentially the Taylor-Pryman constraint, except that the quantity that is constrained is not the velocity anymore, it's the compound current of mass and charge. So what does that mean? So that current cannot vary along Z, and it cannot diverge horizontally, just like the velocity when you have just rotation. But now if you reopen that, what it does mean is that even though that current does not vary, the velocity can vary with Z, as long as the electric current varies also with Z in a way that compensates it, the velocity variation. Same thing for the horizontal divergence, okay? So what does it mean for the topological constraint? Well, it means that because my compound current is two-dimensional and horizontally solenoidal, it has to follow geostrophic contours of constant height. Typically, the tangent cylinder has to follow a tangent cylinder. So that is essentially a constraint. So those two terms here, so I've expressed that in a simple way, but if you account for the presence of boundary layers, you can have source terms that make the current deflect a little bit, and that would be typically a variation of height with time. So typically if the core moves a little bit, and solidification or melting can do that, then that can deflect the geostrophic contours. Or if you inject current, so if your boundaries are not impermeable or not electrically insulating, then those contours move. Okay? They're not exactly static and following the tangent cylinder. Okay, so let's not talk about that for now. I just wanted to underline, that's my contribution to separability of boundaries and bulk, by the way. I just wanted to underline that the usual constraint is actually only for impermeable and static boundaries. But if you account for movement and permeable boundaries, then those contours change. Okay, so again, the compound current follows geostrophic contour, but the velocity field doesn't. And the electric current doesn't. Okay? Again, they can cross it. So the velocity can cross the contour as long as the current crosses the contour the other way to compensate what's crossing. All right. Now, what does it mean? So what does it mean in terms of if I want to express the constraint on the velocity field only? So this is where I go back to my current formulation. And again, actually, as was pointed out, I can use the current formulation in full MHD. So here, this is the full expression of Ohm's law. And I'm looking at what happens along a geostrophic contour. So here, n is the normal to the geostrophic contour, and s is tangent. So I can use Ohm's law to eliminate the component that is normal to the contour. So here I'm expressing that the component of the compound current along the contour is 0. Okay? And I'm expressing the normal component of the contour. So in using current conservation, I can eliminate the electric potential. So spare you the little steps. We get a constraint that constrains exclusively the velocity field. And the interesting thing is that constraint establishes a link between the component of velocity along the contour and the component across the contour. So what it says is that if there is a magnetic field, and if Elsasser is non-zero, which means we have a Lorentz force, then any flow along the contour induces a flow across the contour. It's a bit more complicated than that because there is a derivative along z, so if that flow is two-dimensional, actually there's no flow across the contour. So that's a little bit more subtle than that. But the main idea is that if there's flow along the geostrophic contour, there's also flow across it. And that flow across it is actually perpendicular. It's actually proportional to the magnetic field. It's controlled by the Elsasser number. All right, how do we verify that experimentally? And this is where the fun starts. Okay, might be on time. So I said earlier that the type of experiment we're looking at is a small device that you put inside some kind of magnet. But if you want to visualize the flow, you need a transparent fluid. So liquid metal is not exactly ideal for that, unless you have X-ray PIV, which is expensive and a little bit cumbersome. It exists, but... So let's say we want a transparent fluid. It also needs to be electrically conducting. And the one that is the most conducting and transparent and the least dangerous is 30% concentration sulfuric acid. It is the least dangerous. It's actually not that bad. I'd much rather work with sulfuric acid than liquid metal. Well, the alternative is ionic liquids, which are carcinogenic. There are all sorts of things. And they're not as good, actually. This is the highest concentration. So the problem is that the electric conductivity is 10,000 times less than a liquid metal. So if you want to recover the same sort of electromagnetic effect, so remember the timescale for the Lorentz force, sigma b square over rho, so it's a little bit lighter, so it's helping, but you have a b square, and you're losing 10,000 on sigma, so you only need 100 times the magnetic field. That's good because you get usually very good MHD effects with 0.1 Tesla, so you only need 10 Tesla. But you need 10 Tesla in a volume that is large enough to host an experiment, which is typically a meter long and 30 centimeters wide. I know only one place in the world where you can get that. It's in Grenoble, where they have giant magnets. So this one is a what's the power? It's a 24 megawatt magnet?
20 megawatts. 20.
20. Oh, it's cheap.
M9 is 24.
Ah, so they gave us the weaker one.
Yeah.
I have to talk to them. Okay. So this is a pretty large thing. The magnet is pretty tall. And the other problems you have is, of course, when you want to use cameras, lasers, and things like that, all that's electronics. None of this works in a high magnetic field. So all of this has to be located somewhere outside. And you also want an electric motor, which doesn't work in a magnetic field. So you have to put all these things outside the bore. So that means part of the equipment is located far above, and part of the equipment is located far below. Typically, the heater, the motor are located here. So this is the experiment. So this is the vessel, the main vessel. So that's about 28 centimeters in diameter, if I remember. We have a heater here, which works with a circulating fluid. This is non-conducting. Of course, none of these parts can be metallic, because if you rotate them, then you get a massive break. So it doesn't help. So it's all plastic, ceramic, glass, and things like that. And because the magnet is very tall, the whole thing is, so in that version, it's slightly under 5 meters. The new one is actually over 6 meters. And all of that has to rotate pretty straight and pretty constant and without wobbling too much. We heat here, so this you recognize a Earth curve configuration, and we have a system of mirrors and camera located outside the field that enable us to have horizontal planes here. And we can visualize the flow in planes that are either close to the solid heater here, which acts as a solid core. So most important, the heater protrudes into the fluid. So that means I have a jump in height here. And so I have a tangent cylinder that develops exactly here. Okay? So we measure our velocities mostly in that region at 2 different heights, one close to the heater and one close to the top.
What is the material for the heater surface?
It's a material called chapal. So it's a ceramic that is heat conducting and electrically insulating. There are various variations of that depending on the patents that are around. Did you find one that is much cheaper and just as good?
Yeah, aluminium nitride.
Yeah.
But Chapal is aluminium nitride and boron nitride.
Okay. So there are. I mean, at the time I think there was just chapal, but I think now there are alternatives. Yeah, so the choice of material is usually a problem for this experiment. Okay, so that's the toy. Now if you look at the regimes, you calculate the various numbers. I'm out of time. Okay, so this is a very low magnetic Reynolds number experiment and a very quasi-static experiment. So no wave, no dynamo. So we get dynamo with acid, of course. That would be great, but that's not possible. And what we've done, we've measured velocity profile, okay? The most important are the radial ones, because so we've got azimuthal and radial components. So and this is obtained for different Elsasser numbers at, I think I've got just 1.3 10 minus 5 Ekman number, and I'm varying the Elsasser number. We see that the velocity increases as I increase the magnetic field. And both the radial and the azimuthal component increase. So it is difficult to verify the exact constraint, but what we can do it in order of magnitude, where we verify so we do some fancy estimate to get the time scale associated to the spatial derivative in the constraint, but I'm not going to go do that detail. So basically we have a term associated to the azimuthal component, a term associated to the radial component, and they should be proportional to each other to satisfy the constraint. And these are the points you get. So that provides us with an experimental verification of the constraint. The interesting thing is that the associated flow essentially goes in at the top and out at the bottom. So there's a meridional flow. It's pretty much axisymmetric. So that means the teleprominent constraint is definitely broken despite Ekman number 10 to the minus 6 or so. And the velocity is typically of the order of the velocity that breaks that constraint is typically of the order of the Elsasser number, which is between 0.5 and 1, roughly, which is planetary. Okay, because we're quasi-static, to be short, that also works with the fluctuations. But because Lie is quasi-static, that also works with the fluctuations. But in the general case, full MHD, it shouldn't. Okay. Just one point I want to make. Okay, I'm not going to show you some pictures. These are PIV pictures. So just one thing. Conclusion on the teleprominent constraint. So that's pretty important because it really changes the way we think about how the flow should be constrained in the core. If the usual teleprominent constraint doesn't hold anymore, then we don't need to think perhaps in terms of the Magnetohydrodynamic permanent constraint. So of course, applying that to the core would require a slightly less simplistic configuration, particularly the field is not uniform, it has a radial component, so how does that change these results? That remains to be seen. So that's what we can get from the Magnetohydrodynamic permanent constraint, essentially. So, and that finishes the talk. So what are the takeaway messages? So in MHD experiments that are relevant to, or try to be relevant to geophysics, there are 3 levels of approximation. QS MHD, no wave, no dynamo. Low RM, you can get wave. And full MHD, you may get dynamo if you're lucky, clever, and have a lot of money. So all of these include magnetic induction, just at different levels of approximation. None of these has no induction, just to be clear. In experiment, most of the time, we're in the low RM regime, but that doesn't mean we don't get wave again. And as we can see, the various levels of approximation can capture phenomena that are relevant to the core, even though we don't have the full MHD regime. In particular, we can capture wave and probably nonlinear waves. You don't need a full MHD for that. The low RM can do it. So, moral of the story, know your timescales. That's it. Thank you.